You know, in the clinical lab, some microbes are just part of the scenery. We see them so often we barely give them a second glance. And Staphylococcus auricularis, a super common resident of the human ear canal, is definitely one of them. But what if this so-called harmless bystander is actually capable of causing some really serious, even life-threatening infections? Well, that's exactly what we're going to dive into today.
Just before we jump in, a quick heads up on our sources. All the info for this explainer was compiled using a Gemini deep search. If you're the type who likes to go straight to the primary literature, and I know many of you are, you can find a complete list of every single source and reference in the notebook document that's linked for you.
I think this quote just perfectly captures the whole story of this bug, right? For decades, we wrote off Staphylococcus auricularis as just background noise. You know, a harmless little piece of our skin microbiota. But now, we're realizing it can be a really nasty opportunistic invader, and that's the big shift we're going to unpack.
So here's our game plan. We're going to follow this organism's journey from the lab bench all the way to the patient's bedside. We'll start with its basic identity, then we'll cover how we actually spot it in the lab. From there, we'll look at the clinical syndromes it's being linked to, we'll dive deep into treatment guidelines, and then we'll wrap up with what is frankly the most critical piece, how we can prevent these infections from ever happening.
Okay, so let's start at the very beginning. To really get a handle on how Staphylococcus auricularis can cause disease, we first need to understand its fundamental biology, where it comes from and what makes it so unique.
So, at its core, Staphylococcus auricularis is a classic coagulase-negative staphylococcus, or a cons, as we all call them. And the name auricularis kind of gives away its favorite hangout spot, the human ear. It was first described way back in 1983, and for a long time, it was just considered a totally normal, boring resident of our skin.
But what's really fascinating, especially from a microbiologist's point of view, is its unique spot on the family tree. See, while most staph species cluster together in these big family groups, Staphylococcus auricularis is a bit of a loner. It forms its own distinct lineage. This suggests it's become highly specialized for living in the ear canal. But this uniqueness is a real double-edged sword for us in the lab. It means our standard ID systems, which are built for the more common cons, can sometimes get it wrong. And that's exactly why we need modern, really robust methods to nail the ID.
And that brings us right into the lab. Look, with any cons we pull out of a blood culture, we face that eternal question, right? Is this thing a true pathogen, or is it just a skin contaminant from a bad blood draw? For Staphylococcus auricularis, getting that identification right is absolutely the critical first step.
On the bench, Staphylococcus auricularis pretty much shows a classic cons profile. It's gram-positive, it's catalase-positive, and it's coagulase-negative. Now, under the microscope, one of the key features to look for is its arrangement in pairs and especially tetrads. That can help you tell it apart from the classic grape-like clusters you see with Staphylococcus aureus. On blood agar, you'll see small white colonies, and it's almost always susceptible to novobiocin, though I will say rare resistance has been seen, which is just a good reminder to never ever hang your hat on a single test. Now, for a more definitive, rock-solid identification, we've got to turn to molecular methods. Your standard 16S rRNA sequencing, well, it often just doesn't have the resolution to tell all the closely related Staphylococcus species apart. That's why sequencing more variable housekeeping genes like RPOB or TOOF is really considered the gold standard here. In our day-to-day workflow, of course, most of us are relying on MaliTOF, which is awesome. It's fast, it's effective, but its accuracy is only as good as its reference library. And for a less common bug like Staphylococcus auricularis, an incomplete database can mean you get a failed ID or a low-confidence result.
Before we move over to the clinic, there's this really fascinating discovery that's worth mentioning. Researchers have actually isolated a brand new Cas9 enzyme from Staphylococcus auricularis. They aptly named it SauriCas9. And because it's so compact, so small, it's a super promising tool for gene therapy research. It's just easier to package into those viral vectors. It's a perfect example of how even a seemingly unremarkable microbe can hold some incredible biotechnological potential. Pretty cool, huh?
All right, so let's move into the clinic and see how all this lab stuff translates into actual disease. How does an organism that has such low intrinsic virulence actually manage to cause these life-threatening infections? Well, the mechanism is almost always the same, and you can think of it as the biofilm device breach triad. First, Staphylococcus auricularis is great at forming a biofilm which shields it from our immune system and from antibiotics.
Second, it needs a surface to grow on, and that's usually an indwelling medical device. Think a central line or a prosthetic heart valve. And third, that very device creates a breach in the skin barrier, giving this little skin dweller a direct highway into a sterile site like the bloodstream. It's the perfect storm. And the clinical consequences of these infections? Wow, they can be absolutely devastating, as these published case reports show. They range from catheter-related bacteremia and peritonitis, all the way to, in the most severe cases, prosthetic valve endocarditis. One report detailed a patient with a massive 19-millimeter vegetation on a prosthetic valve. It's just a powerful reminder of how a seemingly low-virulence organism can cause catastrophic damage when it's given the right opportunity.
So, once we have a confirmed infection, the next massive question is treatment. Let's take a look at the antimicrobial therapy and the kind of guideline-based approach that's required here.
When it comes to antimicrobial susceptibility, it's important to know there are no species-specific breakpoints for Staphylococcus auricularis. Instead, we have to rely on the EUCAST breakpoints for the entire CONS group. The single most critical test here is the cephaloxetine screen. If that comes back resistant, it means we have to report resistance across all beta-lactams. For systemic infections, our therapy is then guided by the MIC breakpoints for big guns like vancomycin, linezolid, and daptomycin.
Now, when we look at the actual philosophy of treatment, there are some really interesting differences. International guidelines, like the ones from the IDSA, often recommend starting with empiric vancomycin for any suspected catheter-related bloodstream infection just because methicillin resistance is so common in Cohen's. But the Dutch approach, which we can infer from their strong antimicrobial stewardship principles, would likely be more conservative. They demand stronger evidence of a true infection, and for susceptible isolates, they would push for using a narrow-spectrum beta-lactam like flucloxacillin instead of vancomycin. But here's the thing they both agree on. 100% source control is paramount. You have to get that device out.
And the stakes get even higher in the pediatric population, especially in the NICU, where CONS are a major cause of late-onset sepsis. Vancomycin is still the first-line treatment, but anyone who's worked in peds knows that neonatal dosing is notoriously complex and absolutely requires therapeutic drug monitoring. Linezolid is an alternative for those persistent infections, but you have to worry about toxicity. And daptomycin is also used off-label, with some small case series showing it has promise for clearing those really stubborn bacteremias.
Okay, this brings us to our final and, I would argue, our most important section, prevention. Because these are almost exclusively healthcare-associated infections, our most powerful tool by far is stopping them before they even have a chance to start.
The strategy is not complicated. It really just boils down to three fundamental pillars of infection prevention. First, meticulous, obsessive hand hygiene. Second, strict aseptic technique whenever we insert or even touch an invasive device. And third, a daily review of every single device in a patient, asking that simple question, is this still necessary? And then getting it out the very moment the answer is no. This is our best defense, period.
So, what are the big takeaways for our practice? First, accurate lab identification is totally non-negotiable if we want to distinguish a true infection from a contaminant. Second, if you do have a confirmed infection, source control, getting that device out, is the single most critical thing you can do. And finally, the most important message of all is that these infections are preventable. Diligent, back-to-basics infection control is our absolute best defense.
Hey, if you found this deep dive helpful, be sure to subscribe to the channel for more explainers on clinical microbiology. We would also genuinely love to hear from the community on this one. Have you encountered any interesting cases of Staphylococcus auricularis in your practice? Share your experiences down in the comments. Let's all learn from each other. And I'll leave you with a final thought to chew on. Staphylococcus auricularis is the perfect example of a quiet commensal turning into a dangerous culprit. It really makes you wonder, as our medical technology gets more advanced and our patients become more complex, which harmless microbe is going to be the next one to pop up on our clinical radar? Thanks for watching.